All right, this is the ultimate in parallel force problems. We have a bar, and there's several forces on here. There's an F1 and F2 pulling down on the ends. There's a 10 Newton force pulling here. You'll see this is 1, 2, 3, 4, 5 units divided up. But then we have some forces here that are working at angles. And this is going to be the problem, because whenever we have forces working at angles, we need to resolve. If you don't remember how to resolve, you should probably watch the video on resolution of forces. We need to resolve these into horizontal and vertical forces. So what we want to do, this is kind of a two-part problem here. The first thing we want to do is we want to figure out what F2 is. So as we remember, we have Herman's three laws of parallel forces, and we're going to use, the first thing is we're going to have ups and downs. We're going to make a table of ups and downs. Well, the downs are pretty easy. We're going to have F1 going down, we're going to have 10 going down, and we're going to have F2 going down. Now, what are the ups? Well, you would say, well, all these are kind of going up, but we're not going to deal with them at angles. We're going to deal with them as resolved types of forces. So this force here is really a force going, I'm going to have to do this in a straight line here. It's a force going over and a force going up. And this one here is a force going over to the left and a force going up. And this one here is a force going to the right and a force going up. And we need to resolve those. I'll put on heads on the arrows, so to the left and up and to the right and up. And we need to resolve these things. And so if you remember, hopefully how to do that we do it quickly. It's always the hypotenuse times either the sine or the cosine of the angle. So this side right here is opposite the angle. So this is going to be 40 sine of 80, 40 sine of 80, and that ends up being like 39.4. And this side here is going to be 40 cosine of 80 because this is the adjacent side. So that side right there is going to be about 7, basically. 40 cosine of 80. What's this side here? This is going to be 60, the hypotenuse, times the sine of 60. That's going to be about 52. And this one is going to be 60 times the cosine of 60, which means that that one there is going to be about 30. And then this one here, this is the opposite side, so this is going to be 50 sine of 20. So that's going to be 17.1. And this side here is the adjacent side, so it's going to be the hypotenuse cosine of 20. So that side there is going to be about 46, about 47. Okay? Now, an important point about this when we resolve these things, like for instance, this force right here, when you resolve them into a force going over here and a force going up, sometimes your drawing fools you. You start thinking that this 52 Newton force right here is like somewhere pulling up on the bar right here at this point. It is not. This 52 Newton force is pulling up at this point right here. This is where this force is pulling on. It's pulling on this point right here. So we can say, let's just erase this force and say that instead we have a 30 Newton force pulling from this point, and we have a 52 Newton force pulling up this way. So this 52 Newton force and this 17.1 Newton force are both pulling up right here at this point. Don't let your drawing confuse you. And if it does bother you, you could have resolved this force differently. You could have resolved it as an up and an over. And this one you could have resolved as an up and an over. And then you would see that both of those two forces are coming up off of that point. So that's just a point that we want to make sure that we understand on that. So what do I have for ups? I have 17.1, I have 52, and I have 39.4. And if I add those all together, I get 108.5. 108.5 equals F2 plus F1 plus 10. And I can subtract 108.5 minus 10 and I get 98.5 equals F2 plus F1. So that's going to help me because I want to figure out F2 first. So that's going to help me in here in a little bit to figure out what F1 is. This will help me. So if I want to figure out what F2 is, where am I going to use as my reference point? Well, I want to use F1 as the reference point because I don't want to know what F1 is right now. So I'm going to use this point right here as my reference point. And I'm going to figure out clockwise and counterclockwise torques. So if we think about, if I'm using this as the reference point, that means any down forces are going to cause this bar to rotate around this way, clockwise. So all the down forces are going to cause it to go clockwise. All the up forces are going to cause it to go counterclockwise. So let's see what we have for clockwise. I have 10 times 1, 2. So there's 20 Newton feet, or 20 Newton meters. I have 1, 2, 3, 4, 5 times F2. So I'm going to have 5 times F2 Newton meters worth of clockwise torque also. So those are the only two forces I had going down, 10 and a F2. What about counterclockwise? Well, I have 39.4, and where is this? It's at the 1 place, so it's going to be 39.4 that way. And then what do I have here? Well, I have 52 and 17 is 69. So I have a 69 force right here going up at 1, 2, 3, 4. So I have 69 times, technically it'd be 69.1, I guess. 69.1 times 4 is 276.4 Newton feet of counterclockwise torque. So that's 1, 2, 3, 4 times the 69.1 would be that. So I can take 276.4 plus 39.4, and then I could subtract 20, and then I could divide that by 5, and I could see that my F2, so I'm going to add these up, and I'm going to subtract the 20 from it, and then divide by the 5, and my F2 should equal 59.2. 59.2. So that's going to be my F2. Okay, so that's the first part of the question. So now what I want to do is I want to figure out how should I, which way should I point F1 so that I have this thing in complete equilibrium, which means not accelerating in any direction and not rotating at all. So the deal here is that I have Herman's second law, which I've never really applied till this problem, where I have lefts. Let's see. Let's go a little different color here. Where I have lefts and rights, and these need to be equal also. Lefts and rights. Okay, because right now I can figure out what F1 is, because I know that F2 plus F1 should be 98.5. So if my F2 is 59.2, I'll just take my 98.5 and I'll subtract 59.2, 98.5 minus 59.2, and I'll get 39.3. So I know that this F1 here is 39.3 going down. But does this mean that I'm completely in equilibrium? Well, I won't be rotating, but right now, do my lefts equal my rights? Well, up here I have a right force of 7. Here I have a left force of 30. And here I have a right force of 47. Which means I have a total right of 54 and a total left of 30. What does that mean? That means that this thing is going to be accelerating to the right because there's a net force of 24 to the right. I need, to make this in equilibrium, I need an equilibrant. I need another force going back this way of 24. So I need 24 newtons to the left. So I want to figure out how I can redirection F1. So right now I have 39.3 going down, and I need also a 24 going to the, that was ugly. I need 24 going to the left, 24. And so what I can do is I can say, let's instead make a force. Let's angle this string here to go down this, yikes, to go down this way, from here down to here. And I can just take 39.3 squared, 39.3 squared plus 24 squared equals, and I can take the square root of that, and I can see that really all I need is a 46, basically a 46 Newton force pulling down at some angle here, and I could do tangent of that angle equals opposite 24 over 39.3. So I could do 24 divided by 39.3 inverse tangent, and I get 31 degrees. So if I take a 46 Newton force and I pull it down here at 31 degrees from where the F1 originally was, from the vertical, then I will have this thing in complete equilibrium. It will not be rotating. It will not be accelerating to the left or the right. It will not be accelerating up or down. It'll be completely in static equilibrium there. So sometimes you need to apply the lefts and the rights if the forces are going at angles to the beam or the boom, which is what we call this bar here. So that might be a movie you might want to watch a couple times to make sure you can get this all figured out. It's a little complicated.